Hello everyone. On behalf of Korea Aerospace Research Institute, I would like to thank Konida for inviting KARI to this web seminar. I'm Dr. Bak. I've been working for KARI about 19 years. I was responsible for preparation Earth station in LEO, low Earth orbit, and GEO, geostationary satellite missions. I'm responsible leading engineers for the development of KDSA, Korea Deep Space Antenna, in KPLO, Korea Pathfinder Lunar Orbiter mission. Now I'm going to present a material titled as Satellite Communication and Ground System. This presentation material was made for KARI International Space Training, which yearly held at KARI site except for this year due to COVID-19. Objectives of this presentation is to provide basic of RF communication related to the mission operation of spacecraft, to provide information to understand RF link calculation, and to provide introduction of KARI ground station and ground network for LEO GEO missions. The reference is the book Satellite Communication Systems, written by Gerard and Mitchell. In this presentation, both frequency spectrum and basic communication structure will be presented as introduction. In the link design, link performance criteria, basic transmission theory, decibel, and link budget will be presented. The remains are COMS, geostationary satellite, launched in 2010. Ground station will be introduced, followed by KARI ground network in LEO mission operation. Introduction. Frequency is the rate at which an electromagnetic wave reverts its polarity in cycle per second. Its unit is Hertz. Wavelength is the distance between wave fronts in space. So wavelength is inversely proportional to frequency. In other words, if frequency is higher, then wavelength is shorter. It means antenna size in higher frequency can be smaller than antenna size in lower frequency with the same antenna gain. I will talk about this picture in the later slide. Frequency band is the ranging of frequencies, and bandwidth is the size of width of frequency band. Generally, frequency band is wider than bandwidth. Bandwidth is related to data rate, modulation, and coding scheme. RF radio frequency. Frequency is a part of electromagnetic spectrum ranging between 300 MHz and 300 GHz. To select the RF frequency, it is required to consider the efficient generation of signal power, radiates into free space, and efficient reception at different points at the diversity. As an atmospheric characteristics, some RF frequencies have a severe absorption due to the resonance in water vapor and oxygen. Both 22.3 GHz and 60 GHz is typically not applied for RF communication. Frequency band is allocated for terrestrial and space purpose, generally from UHF, ultra high frequency. Space purpose application is started. The yellow color box means the shared frequency for both purposes. ITU, International Telecommunication Union, manages a global frequency band. However, since the frequency band is treated as one of sovereign assets, every country has its own frequency allocation table with a strict management. You can refer to ITU website for ITU managed frequency allocation table. This is the basic principle for the communication between satellite and ground station. Earth station for transmitting a source information uplink RF signal to satellite. Satellite downlink, it receives signal to other Earth station to receive the information. It is so simple to understand the meaning of uplink and downlink. This is more detailed system block diagram for two ground stations in transmitting and receiving parts. At the transmission station, the input source data is going into source coding, channel coding, modulation, and amplification with enough out power and to be transmitted to satellite through antenna. In the case of receive station, the downlink signal received at antenna and amplified through low noise amplifier. After that, receiving signal is going into demodulator, channel decoder, and source decoder. In the end, the source data delivered to user. Through link analysis, we can decide the desirable output power of HPA, high power amplifier, and antenna size, the noise temperature of LNA, no noise amplifier. This is the block diagram for onboard transmitter, transponder in general. The uplink signal received at antenna and receiver with frequency number 1. Then the frequency number 1 is converted as frequency number 2 through frequency converter with local frequency number 3. The downlink signal with frequency number 2 is transmitted to ground station through transmitter and antenna. Depending on the behavior of onboard transmitter, it can be called as passive when onboard transponder is only reflecting the signal without any processing except for frequency conversion. If the onboard transmitter converter conducts onboard processing, such as Reed-Solomon decoding or other FEC for the error correction, then the transponder can be an active transponder. Definitely, active transponder is better to the case that transmitting Earth station has not enough out power or noise characteristic is not better at receiving Earth station. However, in the case, the complexity of onboard transponder needs to be considered in terms of cost and operational difficulty. Now, link design will be presented. Link design or link analysis to evaluate link performance in the block diagram shown in the previous slide. Regarding the link performance, signal to noise ratio or bit error rate for probability of error is the criteria in analog system and digital system respectively. This criteria can be treated as a minimum value to get a desirable link. For example, signal to noise ratio should be more than 40 dB in television link. In the case of speech channels, more than 30 dB of signal to noise ratio is necessary. In the digital system, to get a bit error rate, BER, less than 10 to the power of minus 6, bit error per noise plus density should be more than 12 dB. From the link analysis, we can trade off the performance of individual units in block diagram to meet the link performance. When it comes to power plus density at distance R, can be received the power per meter square from an isotropic source with power T. Power plus density can be calculated as power T divided by 4 pi R square. As a numerical example, assuming that transmit power at satellite is 10 watts and distance to Earth is 40,000 kilometers, then the power plus density is 4.9710 power of minus 16 watts per meter square. The value of power plus density can be simply expressed as decibel unit. I will talk about the decibel later. Directivity antenna increased power of isotropic radiator in specific direction. The gain of antenna is the power increased in the particular direction relative to an isotropic antenna. This antenna pattern is generated by using commercial SAM master program. which you can download demo version with charge of free of charge. Assuming a parabolic antenna with a 3-meter antenna diameter, 55% of efficient, the antenna gain of both sides or main lobe is 33.37 dBi at 2 GHz. When the off-axis angle is 3 degrees, the off-axis gain is 24.36 dBi. This is the antenna pattern of 9-meter parabolic antenna. In this case, due to the large size antenna than 3-meter antenna, the both side gain is increased as 42.92 dBi. However, off-axis gain dBi is 70.07 and the difference between both side gain and off-axis gain is 25.85 dB. In the case of 3-meter antenna previous, the difference between both side gain and off-axis gain is 9.01 dB. You can recognize that large size antenna has higher gain with a sharp antenna pattern than small size antenna. Small size antenna has a relatively lower gain with wide antenna pattern than large size antenna. In terms of tracking satellite, small size antenna has a benefit with wide antenna pattern. In the case of small antenna, the accurate algorithm is not necessary to track a satellite, or we don't need to know the accurate orbit information of satellite. However, large size antenna need more accurate tracking algorithm and orbit information of satellite. Therefore, small antenna can place beside a large antenna to be helpful for the satellite tracking. EIRP, effective isotropic radiated power, is one of key parameters in link analysis. EIRP is the multiplication of PT input power of transmitting antenna and GT, the antenna gain of transmitting antenna. Return to power plus density, we can put EIRP into the equation. Then the total power available to a received antenna of effective area is like this equation. It looks so complex. Since the effective area can be multiplication of efficiency and physical area, the received power can be written as this. Antenna gain can be expressed as this. We already know the relation between wavelength and frequency from the previous slide. You can easily antenna gain is any size and any frequency and now. When the effective area is written with antenna gain, the received power can be written as this. In the received power, if we consider the space loss, then the received power can be written as this form. This is the basic link budget equation, and we can have an equation to apply link analysis and now. From the basic link budget equation, we can expand the loss term with several expected causes: atmospheric attenuation, transmitting antenna loss, receiving antenna loss, polarization mismatching loss, pointing mismatching loss, receiver loss, and any other known loss. To increase the accuracy of the link analysis, we should input those losses into the link analysis with more reasonable number. Before going into link budget, I would like to talk about decibel concept. We saw a calculated power plus density with very small number, 10 power of minus 14 in the previous slide. When using decibel, it can be changed as minus 140 dB watt. It looks more comfortable to me. Decibel makes small number to be manageable. Besides, decibel allows link budget to be calculated using addition and subtraction, which is much more simple than using multiplication and division. Regarding the decibel unit, depending on the reference in link analysis, there are two units, dB watts and dBm. dB watts is reference to dB greater than 1 watt, and dBm is reference to dB greater than 1 milliwatt. Since 1 watt is 1000 milliwatt, 30 dBm is same as 0 dB watt. By using decibel, we can write the basic link analysis as addition and subtraction. It looks so easy. We can also write the complete link budget equation as decimal. Basically, link budget analysis is using trade-off design. In my case, I usually use Excel spreadsheets to do link budget analysis. This slide shows major link parameters in link analysis between transmission and reception. In transmission part, HPA power, transmission loss, and antenna gain should be considered. In the medial region, antenna pointing loss, free space loss, atmospheric loss caused by gas, cloud, and rain. In the reception part, antenna gain, reception losses, and noise temperature contributions need to be considered. The plus or minus of each parameter is meaning that the addition and subtraction in link analysis. We now take a look at examples of link budget analysis. We considered a combined uplink and downlink case. For the link analysis, we first calculate carrier to noise flux density C over N0 for uplink and downlink. After that, combined C over N0 can be calculated from each uplink and downlink C over N0. Finally, we get a link margin, how the calculated link performance is over the required link performance. This is uplink case. The ERP of ground station is 48 dB. Uplink losses is 177.3 dB. When satellite receive G/T is minus 17 dB, then the uplink C over N0 is 52.3 dB. It can be calculated as addition and subtraction with decibel unit. This is downlink case. The calculation is very similar to uplink case. We get 46 dB as downlink receiver C over N0. Combined uplink and downlink is calculated with this equation. Then the combined C over N0 is 45.1. It is interesting that combined C over N0 is tracing the lower C over N0 between uplink and downlink. In other words, uplink performance can be lower by using small antenna or lower output of a high power amplifier with cost efficiency. Anyway, the bit error probability per noise flux density, which we treated in the previous slide, performance criteria, can be calculated with combined C over N0 and data rate. The calculated EB over N0 is 14 dB, 14.3 dB. Now we can get a link margin from the difference between the calculated EB over N0 and required EB over N0. The result is 2.6 dB. When link margin is minus value, we try to find the link performance to make the link margin as plus value. Typically, 3dB link margin is reasonable in link budget analysis with considering unknown loss term. From now, I will show several examples of KARI ground station, which has been supporting KARI low Earth orbit and geostationary orbit satellite missions. The first is COMS ground station. DATS, that is ground station COMS mission. It has two functionalities, data acquisition and data transmission. For data acquisition, that receives sense data in L-band from MODCS, which is the onboard transmitter in satellite. After receiving sense data, that's converting frequency as IF band. After that, QPSK demodulation and Reed-Solomon decoding, that delivers the raw data to image processing software through TCP/IP. This is the downlink scheme we treated in previous slide. On the other hand, regarding the data transmission, that's received LRT, HRT CAD data from image data generation software through TCP/IP. After that, that's performing convolutional encoding and modulation followed by transmitting signal in S-band to satellite. This is uplink scheme we treated in previous slide. This is a detailed block diagram of DOTS and TTC of ground station. We use 13-meter parabolic antenna. As we treated in the previous slide, ground station has LNA, SSPA, solid state power amplifier, modem, up and down converter. This is summarized link performance with requirements. In the case of sense data reception, the required bit error rate should be 10 power of -8 after Reed-Solomon decoding. In LRT-HRT transmission, the required EIRP is 57 dB watts. This is the link budget what I did for sense data receiving. The link margin is 4 dB, which looks so good. I skip to explain more detail for each parameter in this presentation due to the time limitation. If you need to know more, please send me an email. I will show my contact information in the last slide. This is the link budget for LRT, HRT downlink, uplink, so-called combined case. The overall CO over N0 is the combined value for uplink and downlink. The link margin is over 3 dB. It also looks so good. This is the picture of RF and baseband units in dots. The two units in the center of this picture are SSPA, solid state power amplifier. This is the picture of received spectrum in IF band. You can see the frequency bandwidth of sense data, LRT, and HRT in this picture. In the case of the LEO, low Earth orbit, the contact time at Korea is around 10 to 15 minutes, depending on the satellite path. Therefore, it is required to have ground network with other ground stations in Arctic region to receive payload data alternatively and urgent command. In the case of Sun synchronous orbit, Arctic or Antarctic station has a benefit to increase the number of contacts up to 12 or even 15. This is KARI global ground network for LEO. KARI contact with the KSAT of Norwegian company to use KSAT station in Svalbard Island. This is network link. There is network link between Daejeon and Svalbard to exchange satellite data. KARI also have its own antenna in Daejeon, Jeju Island, Chuuk Island, and King George Island in Antarctic. In Daejeon, KARI headquarters has several antenna stations for LEO and GEO missions. For LEO mission, 30-meter antenna and 7.3-meter antenna in S-band and X-band has been supporting S-band TTNC and X-band payload data downlink. In the case of 9-meter antenna for LEO, only S-band TTNC can be supporting, and this antenna changed to support GEO satellites recently. On the other hand, another 30-meter antenna is now supporting COMS satellite in S-band and L-band. Besides this 30-meter antenna, two new antennas with 9-meter has been installed and operating for GeoComSat-2 satellite, which is the second generation of COMS. This picture shows the 2.4-meter antenna with radome in Chuuk Island in Micronesia. This antenna is using for uplink, the urgent command to LEO, which is coming to Korea. Urgent command is including the urgent changing of image plan for COMSAT satellites. This picture shows the 1.5-meter antenna with radome in King George Island in Antarctic. This antenna is also used for nominal operation of COMSAT satellite. It is a managed system with remote monitoring and control software. This picture shows the 11-meter antenna in Jeju Island using its S-band TTNC functionalities. KARI used this antenna for the urgent operation of COMSAT missions. This picture shows antenna station in Svalbard site, which are owned by KSAT of Norway. KARI has contract with KSAT for supporting ground network service for LEO and nominal operation of KARI low Earth orbit mission. From this presentation, we reviewed the fundamentals of RF communication. We also reviewed basic and examples of link budget analysis. This presentation shows the link analysis which I did for the installation of COMS ground station. Finally, ground network for LEO mission operation is also explained. That's all for my presentation. Thank you for your attention. Since the allocated time is not enough to cover all the information regarding today's topic, I would be happy to share my contact information with Konida and answer any question you may have. Thank you very much.